This lecture is going to be over section 15.3, the kinetic theory of an ideal gas. I will go over some of the main points here, but I'm afraid that if I go through and talk about some of the finer points of the arguments here, that it might get a little confusing. So I'm just going to state the major points here. And if you want to go through and you want to read the rest of it, you're certainly welcome to do so. But the main points are these. The average translational kinetic energy of N moles of an ideal gas is directly proportional to the absolute temperature of the gas. So the average translational kinetic energy, K for kinetic energy, the TR for the translation, you got N moles here. This is what it turns out to be. This relationship can be expressed for a single particle in the gas by using Boltzmann's constant. So if we know this particular relationship, we can put it to use. We can take this, put it in up here, and it's going to change it around to be this. One other thing that you have to bear in mind is that if we look at gas as just molecules, point particles that are behaving Newton's laws, then the kinetic energy is just going to be 1/2 mv squared. Now, if we're looking for the average squared velocity, then as it turns out, this is going to be equal to 3/2 times kT. Also, for different temperatures, you're going to see this is a higher temperature, this is a lower temperature, and this is the lowest that we have, that the velocity of the molecules is going to have a wider distribution. Not every molecule out there is running at the same speed. Depending on the temperature, you're going to have some that are going very, very fast, others not so much. The lower the temperature, the more that those molecules are going to share a particular velocity in common. So that's what that particular graph is trying to get across. So again, we're going to mention here for the kinetic theory that the assumptions of this model is that a container with volume V carries a large number N of identical molecules, each with mass M. The container has perfectly rigid walls that do not move. The molecules behave as point particles. They are small in size in comparison to the average distance between particles into the dimensions of the container. The molecules are in constant random motion. They obey Newton's laws. And during collisions, the molecules exert forces on the walls of the container. This forces create the pressure that the gas exerts. And in a typical collision, the velocity component that is parallel to the wall is unchanged, and the component v of x perpendicular to the wall does change direction, but not magnitude. And this is a model of that particle wall collision. So the process is to find the total change in momentum associated with each collision, which as you go through and you do that, this is what you discover. You find the number of collisions per unit time for a certain area. So when you do that, here's a very lengthy argument about how that comes about. So the number of collisions with wall area A during delta T is going to end up being this. Step 3, we find the total change in momentum per unit time due to these collisions, and from that, the force on area needed to cause that change in momentum, because a change in momentum is going to be caused by a force. So the change in the x direction with respect to time is going to be related to this. Step 4, finally, we obtain an expression for the pressure, which is the force per unit area, and we compare it with the ideal gas equation. So here we go. You know, pressure is equal to force over area. Pressure we had determined was this. And then you can compare this to the ideal gas law, and then come up with this particular relationship. Again, this is not something I would expect you to know, but this is the argument behind where this thing comes from. Boltzmann's constant is defined as R divided by Avogadro's number. This is also a useful equation that you will need to remember. This is the average translational kinetic energy per molecule, depends only on the temperature, not on any other state variable. Another way to write the ideal gas law is this alternative form. Since we now can introduce Boltzmann's constant into this, we can do that here. And then we replace the number of moles here with the number of particles that we end up having. This is how one goes about finding the root mean square speed. This is the root of the mean of the squares. In other words, this velocity gets squared. We're going to add all of those up, divide by the total number that we have. So that will be the mean of the velocity squared, and then we're taking the square root of that. So that's where the RMS comes from. This is a Maxwell-Boltzmann distribution that we had talked about originally, where the spread of the velocities of the molecules can depend on the temperatures. So those are the main points that I want you to draw out of this section. Again, please work the problems and go over any of the tutorials that they may have here.